All right, everyone. So I'm going to just try to quickly go through L'Hopital's rule, keep this video as brief as possible, in the applications. And it's a relatively straightforward application. It's the application of the derivatives that we're using. It also kind of harks back to where we started at the beginning of the semester with limits. So this is always something that we like to show. And also why derivatives are very powerful, because we have a bunch of different limits that we weren't actually really able to calculate back at the beginning of the course. In fact, I kind of hid some from you because if you weren't able to factor them, you did 0 over 0, then we weren't able to solve them, especially if we introduced exponential functions into the mix. So L'Hopital's rule is you just have to assume that you have two differentiable functions, okay? And then you have to say, okay, if I look at the limits individually, the limit as x approaches some number c for that first function here, I can rewrite that as x approaches c. Of f of x is if f is approaching 0 and g of x is approaching 0, then if I'm considering the limit of the ratio of the two functions, this means this limit would be looking like a 0 over 0, something that we said we can't do because we have a 0 in the denominator. But before, we'd say, oh, 0 over 0, the cue that I tried to teach y'all was to factor. Now we don't have to factor it all, we're just going to have to take the derivative, because what L'Hopital rule says is that the limit of that ratio of the two functions f divided by g is equal to the limit as x approaches c of the derivative of f of x divided by the derivative of g of x. Okay? This also holds if both f and g are approaching infinity at the same time. So we always, before we are ever able to apply L'Hopital's rule, we always have to show that the limit as x approaches c of f of x over g of x, this is always either equal to a 0 over 0 or infinity over infinity. We have to show that first before we ever apply. So let's do an example to start off, and something that we've seen before, and with factoring we can solve. I also want to show you that L'Hopital's rule is going to get you that same answer. So if I plugged in 3 blindly into this, which was kind of our go-to for all of our limits, this would be 3 squared minus 2 times 3 minus 3 all over 3 minus 3, which will end up giving me a 0 over 0. So this is my cue before that I could factor it, which you could. You could see that this limit, I could factor this into, let me do it in red, limit as x approaches 3 of x minus 3 times x plus 1 over x minus 3. Those x minus 3's would cancel each other out, leaving me with the limit as x approaches 3 of x plus 1. And then if I plug in 3 there, I see that it is 4. So this was one way we could do it, but this was only achievable because we had a nice rational function where I had a common factor in both the numerator and denominator. We're going to see we don't have to factor and cancel out like factors to still get that limit thanks to L'Hopital's rule. So remember that we plugged in the value, we saw that this is a 0 over 0. So we can use L'Hopital's rule. Yes, it looks like hospital, but it is pronounced L'Hopital. Okay, so I just need to calculate the limit as x approaches 3, or limit as x approaches 3 of this function. So x squared minus 2x minus 3 over x minus 3. What the heck's happened? Is going to be equal to the limit as x approaches 3 of the derivative of what was on top. So x squared minus 2x minus 3 divided by the derivative of what was on bottom, x minus 3. I do those derivative calculations, and note here, this is not quotient rule, right? I'm not saying take the derivative of the entire function. I am, in this case, saying take the derivative of just everything in the top, divide it by the derivative of just everything in the bottom. Well, so then this is still the limit as x approaches 3, when the derivative of the numerator will end up being 2x minus 2, and in the denominator, the derivative of x minus 3 is equal to 1. This is just the limit as x approaches 3 of 2x minus 2. I know I'm no longer going to have a 0 in the denominator. I'm clear to just plug 3 in. This is a 2 times 3 minus 2, or hey, look, we got that same value that it is 4. Okay. So L'Hopital's rule, as long as I can show that I have a 0 over 0 or infinity over infinity, and my functions are differentiable, which in this case they were, because both in the numerator and denominator I had a polynomial, I can just take the derivative, and I know that these limits will be equal to each other. I muted my phone before I started recording this. Okay. Now, one thing I want you to do when you're practicing this and doing your work, and especially for a test or a written quiz, anytime you use L'Hopital's rule, I want you to mark it. Okay. Especially because once we get to the point where we get comfortable with this, we're probably going to jump straight from that first limit that we had, so the limit of x squared minus 2x minus 3 all over x minus 3, directly to it being equal to the limit as x approaches 3 of 2x minus 2. So what I would want you to do every time is this little LH. Okay, this is our indication to both ourselves and the reader that, hey, the reason why these two limits are equal is because I'm applying L'Hopital's rule. Okay? So anytime you apply L'Hopital's rule, let's just do that LH, especially if you're feeling comfortable with derivatives. And like I said, you want to skip where I drew that red arrow. All right, so let's do another example. This one, now I've kind of gone through it. Let me write that 2x. Nope, I don't want it to be in red. This one, pause the video, try it on your own. Okay, we'll wait just a second. Okay, you should have paused the video and at least attempted this. So we're going to go through it. So now if I let x go to infinity, I'm going to see that I have a polynomial that is odd degree with a positive leading coefficient. And because of that, in the numerator, as x goes to infinity, the polynomial is going to go to infinity. And I also know from my exponential functions, stuff like e to the 2x, that as x goes to infinity, we just see that exponential growth. It's going to keep going higher and higher and higher, and at a very, very quickly, or very, very high rate as x increases. So e to the 2x is also going to be going to infinity as x goes to infinity. So that means this limit is going to be infinity over infinity. Okay? So like before, like I said, the only tools that we've had are factoring. So up until now, we would have had no way to solve this equation, solve this limit. But now L'Hopital rule allows us to do that. Because this is infinity over infinity, and I have a differentiable function in the numerator and the denominator. Exponentials are differentiable, polynomials are differentiable. Then I can apply L'Hopital's rule to help me figure out what this limit's supposed to be. So then the limit as x approaches infinity of x cubed plus x squared minus 1 all over e to the 2x by L'Hopital's rule is equal to the limit as x approaches infinity of the derivative of the stuff on top and divided by the derivative of the stuff on bottom. So again, I'm just kind of taking it step by step. If you don't want to write out this intermediary step and just go ahead and calculate the derivatives and fill them in, you're more than welcome to. Just make sure you're marking that equality with that LH so we know, both you when you go back and look at your work, and me and any other readers, that you're applying L'Hopital's rule. But now I need to calculate those derivatives. Still haven't applied my limit yet, so I'm still considering the limit as x approaches infinity. Well, in that numerator, I'm going to have 3x squared plus 2x. In that denominator, the derivative is going to be 2 times e to the 2x. Let's say, okay, well now plug in x to be infinity. But hey, I still have an even degree polynomial with a positive leading coefficient. So as x goes to infinity, it's also going to be going up to positive infinity. And then that numerator, well, that thing is still going to infinity. I'm just now doubling. Well, you might think, oh, that's an issue, but not at all. Because again, what form do I have? I have an infinity over an infinity, which means I can then apply what? L'Hopital's rule. So I can apply L'Hopital's rule again, take the derivative of the stuff on top and the stuff on bottom, and this time I'm not going to write that intermediary step, because if I take the derivative of 3x squared plus 2x, you're hopefully getting very comfortable with your limits or derivatives now, and you should know that that would be 6x plus 2. And in that denominator, I'm now going to have a 4 times e to the 2x, which again is going to be another infinity over infinity. So I'm going to have to calculate this again. I'm going to have to use L'Hopital's rule again, but it's still okay because I keep getting that infinity over infinity. Right? As long as I have an infinity over infinity or a 0 over 0, I can apply L'Hopital's rule. So apply it one more time. Let's see if I can fit this in well. Down here at the bottom, this will be the limit as x approaches infinity of, let me rewrite that infinity, of 6 divided by 8 e to the 2x, because if I take the derivative of 6x plus 2, I'm just left with 6. If I take the derivative of 4 times e to the 2x, I'm left with 8 times e to the 2x. Now if I plug in infinity here, I no longer have an infinity over infinity. This will be a constant divided by a number that keeps getting larger and larger and larger. And we said, if you remember your limit forms, which if you don't, when you first watch this video, that's fine, but by the end of this, you should. That means I'm keep dividing by a larger and larger number. My values are getting closer and closer to 0. So the limit as x approaches infinity of x cubed plus x squared minus 1 divided by e to the 2x, well, this is actually approaching 0. Okay. What this is telling us is that our growth for our exponential functions is much, 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 much faster than the growth that we get for a polynomial function. And because of that, we're going to keep getting these extremely larger numbers, and so much larger that it's going to end up pushing our overall number towards 0. Okay? So this was another example, and the point of this one is you don't have to just apply L'Hopital's rule once. As long as you keep getting an infinity over infinity or a 0 over 0, you can continue to apply L'Hopital's rule. Okay? Again, that's one of the reasons we love L'Hopital's rule. Now I just want to do 2 more, and these are some popular functions that you usually get introduced to at the beginning of the class to prove something called squeeze theorem, but I didn't get time to cover it. Partially because when we come to L'Hopital's rule, it gives us a much better explanation for where the value is. Squeeze theorem is a nice tool to calculate limits, but again, L'Hopital's rule can do a lot of that work for us with a lot less effort. So let's just do this first one, the limit as x approaches 0 of sine of x over x. Well, if I plug in 0, this is going to be sine of 0 over 0, which is a 0 over 0. So my limit is of the form 0 over 0, which means I can apply L'Hopital's rule. So then the limit as x approaches 0 of sine of x over x by L'Hopital's rule is equal to the limit as x approaches 0 of the derivative of sine of x divided by the derivative of x. Well, the derivative of sine of x is, cosine of x. I'm just imagining you're actually talking to me. Makes it much easier. And then the derivative of x is a good old 1. Which means really I'm just considering the limit as x approaches 0 of cosine of x. And I can just plug in 0, and cosine of 0 is 1. And so the limit as x approaches 0 of sine of x divided by x is actually 1. This value is approaching 1. And similarly for this second one, if I do the limit as x approaches 0 of 1 minus cosine of x all over x, I plug in 0. This is going to be a 1 minus cosine of 0 all over 0, which will give me a 1 minus 1 over 0, which, hey, again, turns into a 0 over 0. So I can apply L'Hopital's rule to this limit. So the limit as x approaches 0 of 1 minus cosine of x divided by x by L'Hopital's rule is going to be equal to the limit as x approaches 0 of the derivative of the stuff on top divided by the derivative of the stuff on bottom. So now if I look at the derivative of 1 minus cosine of x, well, the derivative of 1 is 0, so that's going to go away. Then I need to figure out what's the derivative of negative cosine of x. Well, the derivative of negative cosine of x is absolutely correct, sine of x. And then if I take the derivative of the denominator, the derivative of x is 1. So this means that I'm really just considering the limit as x approaches 0 of sine of x, which means this should be approaching sine of 0, and sine of 0 is 0. So I'll come back to this work before I end the video, but I just want to sum it up nicely, because these are two very important limits that will show up. So the limit as x approaches 0 of sine of x over x, this is actually approaching 1 overall. And the limit as x approaches 0 of 1 minus cosine of x all over x is equal to 0. Okay. So, let me pull that back. That's kind of your nice introduction to L'Hopital's. I know the videos that I'm posting to Blackboard as well give you some more examples of using it. The key thing, again, to always check for is 0 over 0, infinity over infinity. As long as you have that indeterminate form appearing for your limits, you can apply L'Hopital's rule. And you just take the derivative of the numerator, divide it by the derivative of the denominator, and then study that. And there is no, no limit the amount of times I can apply L'Hopital's rule as long as I keep getting that indeterminate form to appear, that 0 over 0 or infinity over infinity. Okay, so if you have questions, please sign up for my office hours. Go into Calendly. You can access the link to Calendly through our syllabus. I have a link to it in Blackboard as well. Sign up for a time, meet for me. They are 15 minutes long. You can set up groups. If you have a couple people you're working with, you all want to meet with me, you can all get together. It'll send you a Zoom link. It'll send me a Zoom link. It'll put it in our calendars, and we'll just click that Zoom link to talk. I've had about a fourth of you probably take advantage of that by now. But please, especially coming into the end of the semester, take advantage of it, especially if you're starting to get a little lost. Okay? So I'm going to stop the recording. I hope you all enjoyed this. I hope this was useful. Send me an email, set up an office hours time if we need to talk about this stuff.